we will learn how to analyze our algorithms, and that too following the principles of priori analysis. This means we will analyze our algorithms before executing them. But how do we analyze algorithms? This is what we will learn in this chapter. We are starting this chapter with importance of algorithm analysis. This is the first lecture of chapter number 2. Let's get started and let's see what are the topics. The first topic of this lecture is importance of algorithm analysis. First, we will learn what is the importance of algorithm analysis, and then we will proceed with an example of finding the key in a list to properly understand why we analyze our algorithms. Let's get started with the first topic, that is importance of algorithm analysis. So why do we analyze our algorithms? The reason is pretty simple. There are many algorithms to solve a problem. Suppose we have a problem and we want to solve that problem, but there are many algorithms available to solve that problem. Out of those algorithms, we need to select one algorithm to solve that problem. Now, which algorithm will you choose? The requirement is to choose the algorithm which is the most efficient algorithm out of all the algorithms available. So the requirement is to find the most efficient algorithm to solve the problem. Now, what is the meaning of most efficient algorithm? The efficiency of an algorithm is measured in terms of time and memory space consumption. So the most efficient algorithm is the one which takes least amount of time and memory space. So this is the reason why algorithm analysis is important. Through algorithm analysis, we can select the most efficient algorithm out of many algorithms available to solve the problem. So now we know the importance of algorithm analysis. Let's properly understand this through an example of finding the key in a list. So let's take an example list which consists of 8 items: 1, 23, 34, 46, 65, 78, 90 and 101. These are the items of this list, and let's say that the requirement is to find this key 90 in this list. How do we find this key? The simplest approach is to compare each item of this list with this key 90. So this is approach number 1. We first compare the first item of this list with 90. Let's say some pointer P is pointing to this item. This means this item is under consideration. We are comparing this item with value 90. As P is pointing to 1, we are comparing 1 with 90. Is 1 equal to 90? No. So we will proceed and move our pointer to this value 23. Now 23 is compared with 90. Is 23 equal to 90? No. So we will proceed and compare 34 with 90. Is 34 equal to 90? No. Is 46 equal to 90? No. Is 65 equal to 90? No. Is 78 equal to 90? No. Is 90 equal to 90? Yes. At this point, we found the key. 90 is equal to 90, and this means key is found. How many comparisons we took? A total of 7 comparisons. 1, 2, 3, 4, 5, 6, 7. So the total number of comparisons is 7. These many comparisons we took to find whether the key is available in the list or not. So this is approach number 1. This is not the only approach. There is a smarter way to find a specific key in a list. Now let's look at approach number 2. In the approach number 2, we will start from the middle of the list. How do we find the middle of the list? By dividing the length of the list by 2. What is the length of this list? Length of this list is 8. 8 divided by 2 is 4. So our pointer P should point to the fourth item. This is the middle of the list. Is 46 equal to 90? 46 is not equal to 90. At this point, we are done with one comparison. 46 is not equal to 90, but 90 is greater than 46. We can observe this that the list is in ascending order. This means items are arranged in ascending order. This means there is no chance that 90 can appear before 46. This means this half of the list can be eliminated. We can remove this half because there is no possibility that 90 can appear in this part of the list. Hence, we can remove this part from this list. We will be left with the remaining half of the list. With just one comparison, we have removed the half of the list. Now we are left with the remaining half. We are left with just 4 items. Previously, we were having 8 items. In this list, the middle element is 78. Why? There are 4 items in this list and 4 divided by 2 is 2. So, second element is the middle. Now, let's compare 78 and 90. Is 78 equal to 90? No. At this point, we are done with one more comparison. So, total number of comparisons at this point is 2. Pointer P is pointing to 78. That's why we are comparing 78 with 90. Clearly, 90 is not equal to 78, but 90 is greater than 78. Hence, there is no chance that 90 can come before 78. So, we can eliminate this half of the list. And we are left with this half. Again, we will calculate the middle of the list by dividing the length of the list by 2. We will get 1, which means that the middle of the list is the first item. Now let's compare 90 by 90. Is 90 equal to 90? Yes. At this point, we found the key. And also, the total number of comparisons at this point is 3. So we found the item with just 3 comparisons. So approach number 2 is faster than approach number 1. In approach number 1, we took 7 comparisons to come to this conclusion that 90 is available in the list. While in this case, we took 3 comparisons to come to this conclusion that 90 is available in the list. So clearly, approach number 2 is faster. I hope this concept is clear. We got a faster approach to solve the same problem. This means we got a faster algorithm. Although the difference does not seem much, because the length of the list is not that much. It is just 8. What if we take 100 integers? Then we will see the difference. Before that, I would like to mention this, that approach number 1 is linear search. The term linear refers to the fact that we are searching this list linearly or sequentially. This means each item is compared with the key. On the other hand, approach number 2 is binary search, because every time we are dividing the list by 2, initially we were having 8 items in the list, then we were left with 4 items, and finally we are left with 2 items. So we are dividing the list by 2 each time. This is the reason why this search is known as binary search. Binary means 2. We are dividing the list by 2 each time. So, this is linear search and this is binary search. Linear search is slower than binary search, that's what we can observe. But the difference will be much clearer if we take more integers. Let's take 100 integers. What if we have 100 integers in a list? Let us assume the worst case. Let's say that the item that we want to find out is available at the end of the list. Then in that case, linear search will take 100 comparisons to come to the conclusion that the item is available in the list. It will take 100 comparisons. What about binary search? Can you guess how many comparisons will be there? There will be 7 comparisons only. Only 7 comparisons. Can you see the difference? Binary search is much faster than linear search. As the size of the input increases, we can observe that binary search has shown a drastic increase in speed. Why is this the case? Because we are dividing the list by 2 each time. We start with 100 integers. Then we are left with 50 integers because we are dividing the list by half. Then we are left with 25 integers, then 12 integers, then 6 integers, then 3 integers, and finally just 1 integer. A total of 7 comparisons are needed to come to the conclusion that the key is available in the list. Eventually, we will end up with 1 integer, and that integer will be the item that we are looking for. As mentioned, we were assuming that the key is available at the end of the list. So, the integer that we will get at the end will be the item that we were looking for. Every time we are dividing the list by 2, and each time we are comparing the middle of the list by the key that we want to find out. This is the reason why binary search is just taking 7 comparisons to come to the conclusion. So clearly, binary search is much faster than linear search. I hope now the importance of algorithm analysis is clear. As I have mentioned, there are multiple algorithms to solve a problem. Here the problem is to find the key in a list. And the approaches or the algorithms are linear search and binary search. We come to this conclusion that binary search is faster than linear search because it takes less comparisons compared to linear search. So we analyzed these 2 algorithms and come to the conclusion that one algorithm is better than the other. And this is what we want. We want the best algorithm to solve the problem. And we come to the conclusion that in order to find a specific key in a list, binary search is more efficient because binary search needs 7 comparisons. This is way lesser than the 100 comparisons needed for linear search. So with this, we understood the importance of algorithm analysis, and this means we are done with this lecture. Okay friends, this is it for now. Thank you for watching this presentation. I will see you